Hello everybody, welcome to component-based software development. This is the second week, which means today I will give you two lectures and finally introduction to guide you how to do your mini project. So I hope you review the slides I taught you last week so you can carry on. Well, the third lecture is about CBD life cycles. CBD is component-based development, of course, if you still remember that. Yes, and okay, let's begin with a question. State three things about software life cycles and how they can be applied to CBD. Well, the things, of course, what you know of, right? Which means you must know something when you are undergraduate student. You must learn something about software life cycles, right? This is the basic knowledge of software engineering. So this question just to remind you, try to make you memorize what kind of software life cycles you have learned, and if you know that, we can keep talking about what's the difference between a CBD life cycle and a normal software life cycle. So, as usual, I will give you 1 minute to think about that. Okay, start now. 1 minute, think about the software life cycles. Okay, time's up. Well, let's see what you know, right? Okay. So first, what is software life cycles, right? To memorize what kind of software, what kind of software life cycles are there, you must know the definition of software life cycles, right? So software life cycles, basically, it defines the development process, right? It is a process followed for a software project within a software organization, and it consists of a detailed plan describing how to develop, maintain, replace, and alt or enhance specific software. So, therefore, the life cycle, it defines the methodology for improving the quality of software and the overall development process. So, well, a software life may be sequential, maybe iterative, or maybe agile, right? So, how many steps, how many stages or phases in a software life cycle, in a normal software life cycle? Well, some of you maybe say it was 6. Some people, some of you maybe tell me 5, and some of you maybe say 4. It's all right. It depends how you divide the phases. But normally there's 4 big parts. Okay, 5 big parts. Okay, the first one, of course, is the analysis, which is it lets the developers or the customers to define the requirements. Right, the requirements given by the customers must be understood by the developers, software engineers. So therefore, the first step is always the analysis. To analyze the requirements, and after that, after you understand the requirements, the second one is to design a system according to the requirement. Right. The second one is always the design, and the third one is implementation. Therefore, you should know in the standard software engineering, implementation is always after the designing. So you must have a blueprint of the system. Then you can develop it to code, to write some code for it. And after the implementations, the fourth step is testing. Right? Evaluate your software, to test it, to verify it. And finally, the five parts. Well, in some book, I know in some textbook, it didn't say the 5 stages, which is the maintenance. Okay, well, the reasons it is say some people don't think maintenance, sustaining the software system is not a part of the software life cycles because it is beyond the development phase. Well, it makes a little sense. However, well, if you think this, well, from a software engineer perspective, you will say, okay, maintenance, of course, is an important part in the software life cycles. So it could be 4 or 5. Well, what's the 6? Some people say, well, some book it describes the software life cycles as a 6 stages process, because in the analysis, they said it was not just analysis. It also the analysis and the definition is different. So you mean analyze the requirements and then define the requirements is different. Well, it makes a little sense, but whatever. You should know, just should know how many parts you have here. Well, like we described on this slide, a software life may be sequential, maybe iterative, or maybe agile. Of course, sequential is the easiest one, so everyone can understand it. Now I'll show you a sequential software development life cycle model, which calls water flow model. So of course, I think everyone knows that, right? Waterfall model. The waterfall model, well, actually it is very old. It is classic, which means it is very old. It is published in 1970. 1970 means, well, in 1970 there is barely have a programming language, a real programming language, and the people in 1970 they're already thinking about software engineer and give us the waterfall model. So waterfall model is a sequential, and the reason we call it waterfall because this model emphasizes a logical progression of steps which are taken throughout the software development lifecycle, much like the cascading steps down an incremental waterfall. Well, it is a little, odd to say that, but well, I think you should understand what I mean, right? So step by step, each step we do things according to the output we get from the last steps. So of course, requirements here in the design and the implementation, and this one is called verification, which means testing and evaluation, and the final name maintenance. This is a very standard 5 stages process of software development life cycle, just like I said before. So the problem in this waterfall model is there is no pre-existing components, right? So if you want to do some components, it is a problem. You want to implement, you have to design it, and you want to design it, you have to understand it from the requirements. So there is no pre-existing components for that. And people find it is maybe not the best model they want, because well, still it takes you a lot of effort and time. The efficiency is a problem. Therefore, they make a new model after the sequential one. So the second one is an iterative model. Iterative means loop, right? Circle. Just what we described here. When you see the circle here, you should know the input is a planning. See, I plan to do something, and I analyze the requirements here. After that, I design. Again, we design with implementation, and if the system is fine, for example, the requirements are very simple, so the design is simple, the implementation is simple, so we can finish it here in the first loop, and the deployment and run it maybe. But if it is a little complex, it's a little complicated, we should testing, we should evaluation, we should find the flaw, find the defects of the system we built, and the planning again, and the requirements again, and do the analysis, and do the design, and finally finish the implementation again, and again. So this one, it becomes a loop. We recursively do these steps to do the process until someday we find it is, well, it is perfect, or it is satisfied the customer's requirements, so we can deploy it and finally release it, publish it. So this is iterative model. You just remember there's a loop inside the iterative model. So after iterative model, there's another thing called V model. The V model is a new progress called V model. This one, the iterative model, well, each loop we implement, let's say we incrementally improve the system. So it already has a little idea about component-based development, because he know it is incremental. So people using this model already know a system should be built part by part, right? Every part is incremental, part by part. So I will say it is a very early idea of CBD. And this one called V model. V model is a new progress. It's a progress. The V model represents a development process that may be considered as an extension of the waterfall model. Right? Looks like waterfall model is like this, one line, up to down. However, V model, just like you fold the waterfall model in the half, in the middle, so it becomes a V. See, it looks a V, up, down, up. But the reason we have to fold it to a V, make it to a V, because it demonstrates the relationships between each phase of development of life cycle and its associated phase of testing. So the V model actually, well, take testing into account. Like before, we didn't pay more attention about testing, but here, finally, we see, wow, testing is important. Testing is important. So for each phase, concept operations, requirements, detailed design, and we have testing for that. So the related testing will give a feedback after each one. After each one is performed, each stage is performed. Well, we will discuss more details about V model later, because V model actually is closely relevant to our CBD life cycles. So we will leave a little surprise later. Okay, so we'll discuss the detail later. So let's carry on. So what is the CBD life cycle? Right, what's the difference between the CBD life cycle and just a single individual system life cycle? Right, what's the difference here? So this diagram, we already see that before last week if you review the slides. The components, and here's a repository, which means the components must be built first It must be built first. Then it was stored in a repository, or it's deposited in a repository, and the system will use it or reuse it, just like for example A here. We reuse the A. We use the A in system 1 and reuse it in system 2. So the system, if we want to develop a system, we don't need to do it from scratch, right? We just use it or reuse it, reuse the components from the repository to building many different systems. So CBD life cycle, it looks like CBD life cycle is very similar to a traditional software development life cycle. However, the system's life cycle makes a little difference, right? Have a little difference. Therefore, we must know what is the CBD desiderator. This word is a little, I know, fancy, right? Desiderator. This word, I think it was Latin. It is to people who don't understand this word. This word is not letter. Sorry, it's a word. This one means the things you really need it. The things you really need it. Okay. Okay. The CBD desiderator. First, CBD present and the feature. What's the CBD present? So the taxonomy of components model shows that the CBD component models will have give you a brief presentation last week. So it should show you current component models also do not fully meet the CBSE desiderator, CBSE CBD desiderator, and the new component models proposed, and it makes the taxonomy expanded. However, in the future, the CBD faces new challenges: increase the scale, increase the complexity, and increase the safety. So it have to meet the new desiderator. So what's that related to our CBD life cycle, right? So actually it has a relationship, because nowadays we know there is at least 6 desiderator of CBD. The first one, components should pre-exist, which means before you develop a system, you should do components first. You should already have the components. Therefore, the components should be produced independently, which means even you don't have the system, even you don't think about the system, even you finally decide not to develop a system, it doesn't infect you to infect the development of components, right? So therefore we can guarantee the components can be reused. So there's no coupling between components and the systems. So every component should be produced independently. And it's not enough. We also have to make sure the components should be deployed independently. Right? What's mean deployed independently? Like a plug. You can just plug into a system. Make a system is assemble the components. So easy to use. So if you can do that, it still becomes a very closed part of the system. So it is still have the reusability is still very low. So the third one is deployed independently. The fourth one, it should be possible to copy and instantiate components, right? Because we want to reuse the components. Therefore, for a component, it should be an individual object that we can copy it. We can make a new instance of it, so we can use it in a new system without infect the existing one, right? Just like the example, system 1 use component A, system use component A again. It actually use the instance of component A. Right? We create component like a data type. maybe we can call it component type. Every time we use it, we actually make an instance, then use it. So this is the fourth desiderator. And the the number 5, it should be possible to build composites. What is composite? Composite means, well, we use components to build larger components. Right, so it's called composite. Right, composite component. So if you can do that, well, which means your component is not flexible enough to be extended, which is also very bad because it will affect the maintainability, affect the involvability of the system, of course. So you should be using components to build larger ones. And finally, it should be possible to store the compositions. So like another circle, when we use components to build larger components, these components should be pre-exist again and produced independently and deposited in a repository. Therefore, the composite component can be deployed independently again, can be copied and instantiated, can be built again. Right. So this six conditions actually, they are the CBD desiderators. And if you study that, you can see each of one is closely related to the CBD life cycles. Therefore, the CBD life cycles, it looks like that. The components need their own life cycle. Of course, this is our conclusion. The components need their own life cycles. So now, before we have waterfalls, right? There's a one-way waterfall. Now it looks like we have a parallel development process. Here, still we have the requirement analysis. After that, we have to make some designing job, and then here, in a component development, we still do implementations. We have to write in code, right, to compile, to build the components. Then we have to test in components, and finally to maintain these components. But in component-based system development, here we don't have implementation anymore. We have the component selection, right? Which component we can use, and if we want to use it, we can just retrieve it from the repository. And this one, component adaptation, which means maybe we can just tweak the component a little, change a little to make it fit our system. So it's called adaptation, right? Sometimes we cannot guarantee our components 100% to perfectly fit our system. Therefore, we need adaptation. And finally, we need component assembly, because ideally a system, well, if we do it right, we don't actually need to writing any code for a system. We just assemble the components it needs to make to construct a system. However, well, normally in most of the cases we still need a little glue code here. Of course, we didn't write here, but maybe still need a glue code for component assembly. Then test and maintenance. So it becomes a branch here. The two different kinds of development process happens here. So what should we do? What should we draw of the? If we draw a picture, can we use one picture to describe the orders, to describe the life cycles of a component-based system development, right? This one, even it makes a little sense, but it doesn't look like a valid life cycle, right? The diagram didn't show the valid life cycle here, so we still have to make a model for that. So this is the question, the next question: can we use the waterfall for both component and system life cycles? Why or why not? I maybe accidentally already tell you the result, the answer here, because here I already tell you it is not possible, right? It is not possible. Waterfall, it is one way, up to down, or say top to bottom is much better. Top to bottom. However, here we have a branch here, so it doesn't make sense. We can parallel, right, concurrently do the two different life circles. So waterfall is not enough. It doesn't satisfy our requirement. So we need a new model. So okay, so I give you 1 minute for this question. So next one, what is the idealized component life cycle? What is the idealized component life cycle? First, we're just comparing it to traditional system software development life cycle. Before we said we have a phase called design, right? We have to design the software architecture. Yeah, we have to design to make sure what kind of the functions we should have for the system, how we should implement it, then we have to implementation it, then we have to testing it or something, right? But in component here, we still have the design. Component design, I gave you some, this is some very cute pictures to shows the software engineer, they try to design the component, and this one making it very clearly. We design it, we build it, and finally we deposit our component in a repository. And this one is the deployment. What's deployment here? What deployment here? See, we search what component we want, we retrieve it, and we use it to build system. So this is part is called a component deployment. And then finally is component execution. Right, the components are executed at a system runtime. Well, just like the gears. Well, it will be run one after another when all the system is activated. So there is 3 main life cycles in 3 main stages in the component life cycle. Right, of course, it's idealized. So this one we use it. We explain the idealized component life cycle in a very in the plain English, right? To give you a picture, to let you know how to describe it. Then we should do it in a more formal way to tell you what the idealized component life cycle looks like. Right. First, let's look at the picture on the right side. Here, the right side. Right, okay. In the right side, there is design, deployment, and runtime. Just like we said it before, design, deployment, and runtime execution. And there is 4 different. Yeah, what's this? Environment, right? 4 different environment. In design time, we have a builder, we have a repository, and in the deployment time, we have assembler. In the runtime, we have a runtime environment, RTE, runtime environment. So, what is a builder here, right? Builder is a tool for designing and building components. For example, if you're using Java Bean or EJB, what is the builder? The builder could be Eclipse, right? Eclipse is a tool. Could be NetBeans, right? It's also a tool for EJB. But if you use .NET COM, the builder maybe is Visual Studio, right? So it's a tool. So the repository is it's a like a database. It allowed you to deposit your components. So people may ask, what database can allow us to deposit components? Because usually components are objects, right? So actually, we can of course, if we store the code, we just store the inner code, we can use NS database. But nowadays usually we use some NoSQL database like Mongo, right? You can just allow you to deposit an object completely, well, in a complete manner. So the repository here, now we have many choices. And the assembler also is a tool for building systems by assembling components, the components we retrieved from the repository. So the assembler maybe is the same tool. Well, usually it is the same tool of the builder. We give it a different name because it just to remind you it belongs to different phases, different stages in the life cycle. But usually we do it in the same tool, just like the builder. Of course, we can, well, if we have a work in a very big team, or we can have different choices, different options. For example, like still using the EJB or Java Bean, like as an example. If I like NetBeans, I can build a NetBean, a component using NetBeans, the very famous IDE. Well, and some people, my team, my colleague, he can retrieve a component from the repository and use it to assemble a system in his Eclipse. It's also fine. So the assembler and the builder, they are not the same thing. Here they are not the same thing. And finally, in the runtime environment, we're just executing of the deploying components. Right, the runtime environment can be just a different environment. Can be, well, backend, it can be front end. Well, it depends what kind of system we write. We implement it. And here there are some notations, there's some legends I want you to remember here. This one, of course, is the component, right? This is the component, the blue blocks components, and this is the component binary. Component, this one means it may be binary. So assembler, sometimes we didn't just put the original component into the assembler. Sometimes we're just using the binary component, means we already compile it in the assembler. For example, well, NetBeans here maybe not a good example. For example, if you're using C#, using .NET, right? We know if you're using C#, you will, when you do a component, you will create something called, when you compile it, you will create a new type of file, .dll, right? .dll is something after you compile a component, and the next time, actually, you just need to repository the DLL file in the you just deposit the DLL file in the repository, and another one, or later you want to reuse it, you can just retrieve a DLL file of A here in your Visual Studio again. You don't need to know what's the exact code in component A. We don't need the exact, the original component A, just the DLL file. So this one, the yellow block, is component but maybe binary, right, in a binary form. And this is, of course, component instance. This one, the brown one, component instance. So in the runtime, we're always using the instance of components here, inst A, inst B, inst C, inst B, C. So what is this one? This is a composition operator, means here, when we build B and C, we can build a BC and deposit BC in the repository directly. And here, the red block, red square, the red square, means it is another, it's also a composition operator, but here we can composite binary component in assembler. Well, which is, if we cannot do that, we want something composite in assembler. It is complicated. We have to retrieve it to builder and composite it and deposit in repository again and retrieve it in the assembler. But if we can do that, we can compose the binary component in assembler. We don't need to do this again. We don't need to go back. Right? We just here AB, yeah, something like that. Then give it to the runtime environment. However, you must remember, this is called idealized component lifecycle. Idealized, which means in the best scenario, if you have a perfect component model, we can do that. But do we have it now? Right? Do we have it now? Yeah, and I will give you the answer now. Okay, I can just give you the answer. No, we don't have idealized component lifecycle. We have something similar like this. We have something a little weak than this, and maybe someday you can invent something like this. Okay, so this is our ultimate goal for the components-based development, software development, to invent a idealized component model. Right. So now we know. Let's make a quick conclusion. Right. This is the diagram. This is the idealized component life cycle, and this is the demonstrator. And let's see if the idealized component life cycle meets the CVD demonstrator. Okay, we said there is a 6 demonstrator, right? This should produce independently. Well, in the idealized component, in the idealized circle, yes, in the design phase of a builder, yeah. Components pre-exist. Sure, we have the repository. Repository means we can development components and deposit it. So yeah, pre-exist, done. And the deployment phase, yes, because the repository is available. So yeah, done. Runtime, of course, we don't need runtime here. Components deployed implementedly. Can we do that? Deployment. So let's look at the deployment phase. Yes, we have something called assembler. So if we have the assembler, we can deploy the components independently. Yes, so done. So components can be copied and instantiated. Can we do that? In the design phase, of course, C, B, and C composed. See this one, copies. Right? A can be copied, B, C, they can both be copied. Right? And the deployment phase, yes, we can also copy it. We can also copy it for different systems, of course. And in the runtime, we have the instances are possible, which means even we only have one copies for here, we can run the system. We can run the system in different instances, right? So in the runtime, yeah, we still have the instances. We can still make a new instance, make many new instances. So yeah, so components can be copied in design phase and the deployment phase, and instantiated in runtime phase. Yes, composites can be made. Can we make them? Yeah. So composition possible. See this one? Yeah, this means we can composite B and C in builder. So a design phase, deployment, composition possible. Yeah, we have something called the deployment phase composition operator. So yeah, it's possible. And in runtime, maybe that is not possible. Maybe that is not possible. So here we just say this one. Here we just say we just like the one we used in assembler. Actually, this one is a composite in the assembler in the deployment phase. So, but usually I don't think we actually will need composites in runtime phase. Maybe we don't need it. Well, maybe we need it in web service, maybe. Okay. Finally, composites can be stored. Can we? Yeah, we have the repository. Yeah, it can be stored. Of course it can be. So in the design phase, yeah, the repository is only in the design phase. Yeah. So according to the idealized component life cycle, it almost, I think it meets the CVD desolator. So the problem is, can we actually make this one? Right. So we back to the original, or to the previous question. Can we actually meet this? Can we actually implement a component model that satisfy all the conditions here? Okay. Actors and artifacts in the idealized component lifecycle. This is also a conclusion, right? Design phase, deployment phase. What's the role of defined design phase? Is this a component designer? Well, if it's not designer, if it's a producer, vendor, which means in design phase we can design our components or just ask someone, the third party, to give us one, right? In the deployment phase, what's the role of the deployment phase? System developer. So which means whoever develop the system actually only need to consider right, deploy the component deployment here in the deployment phase. So the environment, what's the environment design phase? System independent. This is the environment. But in the deployment phase is a system specific. So in the design phase, we don't need to consider, we don't need to think too much about what is the system. Right? We just focus on the components development. But here in deployment phase, we have to do everything that satisfy the system's requirements. Component type. Here in design phase, we actually is a template and the deployment contract. Right, templates is just like the thing the component will deposit in the repository. Deployment contracts means with the conditions of what kind of deployments are valid. So this is the only thing we need to think we need to consider that in the design phase. And the deployment phase, it is just like deployed subsystem, right? Because we deploy the components, right? Nested composite components. Every nested composite is a subsystem of the system, right? The data in components in design phase. What is data in components? Placeholders, which means for every component we already have the semantic of each component. For example, the interface are fixed, right? The format here is fixed. All we need to do is to fill the blank, which is writing the code in the computation part. So this is the data in component. In design phase, it's just the placeholders. We have filled the blank, that's fine. However, in deployment phase, not just the placeholders, we also need to configuration data, right? Data between the components, so we need to configuration for that. And this one, component format, here we're using source of binary, like I showed you before. The source in the builder, the binary in the assembler. But in the deployment phase, we only need with the idealized scenario, we only deployment binary code. Right? We don't need the original object. Binary is enough for the deployment. Composite operator in design phase, it is predefined. In deployment phase, it's also predefined. Well, this one is related to component, related to component semantic, the semantic of components. So the operators, it shows the composition mechanism, right? So it should be predefined. And finally, interface generation also, just like the composition operator, it shows you the composition mechanism. So yes, so it should be here and here. They should be both yes in design phase and the deployment phase. So this is another conclusion of the idealized component life cycle. But here we focus on the actors and artifacts in these two phases. Alright, so you should memorize this table, it's very important. Right, okay. Now we can make new details of the life cycles for CBD of this diagram. First, we add a domain knowledge here. What's a domain knowledge? For example, if you want create let's say you want to do a medical application, right, to do the diagnosis, auxiliary diagnosis. You must know what kind of disease you're dealing with, right? So what kind of parameter will let you to diagnose a disease, right? Something like that. Domain knowledge is the background. It may be not very functional requirements, but it is the background of the system, which means if you don't know that, you probably will not get the right system. Right, and we use the the color blue for the background, because usually domain knowledge is not just finished by the not just acquired by the developer. We need help from the domain expert. Right? For example, want to do a medical application, usually we need help. We need help from doctors, right? So after domain knowledge, after we know enough domain knowledge, we do the component design. So this is the prepare task. Then we can do component design to define the knowledge, right? To analyze to do the analysis, to analyze the knowledge, analyze the requirement, see what kind of knowledge we can use here, and send here. Then the system requirements will becomes to the component deployment. Right? We have the requirements, we know the requirements, so we decide according to the requirements, we decide which components should be used. Should be searched, should be retrieved, should be assembled. So the system requirements finally leads to system assembly, and the finally component execution, which leads to system execution. Right, we execute all the components in system, which means we are actually run a system. So it's in the runtime. So this one give more details about the life cycles of CBD. We actually merge the CBD life cycle and the system life cycle in one picture. Here. So again, use a better picture, use a former picture for this component life cycle for a domain here, domain knowledge, component design, which means design and implementation of domain specific components and the connectors. Connectors is something you connected components for composition, right? Putting the repository and the component deployment of components in a specific system. Here is the system lifecycle. It was for one system. System requirement, system specific, component selection and adaptation, which is highly related to this part. We should do that after we retrieve something from repository. And after we retrieve something repository, the component we deployed will go back here, let us to do the final step, system assembly. Then system assembly, which actually the output of the system assembly is the composition of deployed components. And the composition of deployed components is with so-called software architecture. This is how we get software architecture. So this is a better diagram of life cycles for CBD and component-based development, including component life cycle and system life cycle. Okay, carry on. So the next question, give an example of a domain and indicate some components for that domain, as well as systems that can be built from these components. This question is highly related to the mini project. If you, well, watch another mini project video later, so, well, you should really think about that, right? 1 minute. Right, I'll give you the example of a medical application, which is currently I'm working on, something I'm working on. However, in the mini project, you can do anything you're familiar with, of course. Okay, I leave some. I leave the I will leave the details in the mini project introduction. Well, you can think now, right? Of course, you should think now. Okay, time's up. So, finally, this is the key of this lecture, or the core of this lecture, the thing we want to learn from this lecture. What is the model of CBD life cycle? Finally, the answer is here, the W model, which actually is a V and V model, right? The two V's. We merge two V's and it looks like a W model. So this is the life cycle of CBD, of a component-based system. Right? This is using W model. So the first V on the left side, well, we can see there is the life cycle of component development. And the second V on the right side, it was the life cycle of the system. Yes. And the merge point, the purple one, the purple block in the middle, is a component selection and adaptation. So W model is adapted from V model. So do you still remember the V model here? Yes. Let's have a little review of the V model. As I said before, the V model, it was connect the activity of the process and the testing. For example, here, system requirements. When we analyze the system requirement, we not just give some result of the analysis, we not just analyze the requirement, we also design the acceptance test plan, and for the final testing, acceptance testing, the system specification, which we are doing when we define the requirement. The output is a system specification. System specification means you already know all the behavior. Usually we can using some document to organize the behavior, to format the behavior. And here we are not just give a specification to the next step, we also have to design some test plan for later testing of system testing here. See, then the specification, when we're using the specification for architectural design, we also do an integration test plan for integrating system testing. The module design, which we are design the component, we also make a unit test plan for unit testing. And finally, this coding. After coding, we can do the testing, which means the material of testing is reused from here the development phase. So this is the real means, the real idea, the true idea, the true concept of the V model here. Here the unit testing, integration testing, system testing, acceptance testing, which is the standard testing suite. This is the standard testing. They're together, they are a standard testing suite where we test our system from the tiny granularity, from the bottom, which means the smallest granularity to the highest granularity. Unit testing we're using to test component, right? Not maybe just a component, even the functions in the component here, because module design actually designed what a component looks like. So unit testing is testing the functions and this component, the functions within the component and the individual component behavior. Then the integration testing, we're not just testing a component, we're testing a composite component, which includes the functions, the interfaces between we use in the component, right? This is called integration testing. And finally, system testing is for the individual testing. Yeah, for the system, see the functions. See everything, we give a right input, can we get a right output? See, is every functions correct in the system testing? And finally, acceptance testing, which means we evaluate the system, not just testing, not just the functional correction. We also need to see if the testing, if our system satisfied the non-functional requirement, right? Just like performance, right? Efficiency, time consuming, something like that. Acceptance testing. If you don't remember the testing part, you should review the software testing. You should give you a chance to restudy the software testing, which is pretty important in software engineering, right? So this is the V model, and this is the W model. Here, because the limitation of the space, we omit the arrow here. So yeah, there are still arrows here. System requirements, acceptance test plan here, system specification, system test plan, and here system assembly, compositional V and V. V and V means what? V and V, yeah. Verification and validation, V and V. Verification and validation is not, it's similar but not quite the same. They have a subtle difference. So yeah, you should know that. All right, you should know that. System assembly, compositional V and V is for what? For unit test integration. No, it's for the integration test plan, right? So where's this one? Unit test plan. Where's this one? Unit test plan is in this V here. When we do component design and the component V and V, this is the unit testing. So the V should be like this, and every time we do development part, we already make a preparation. We are ready to be tested, or already prepare our testing cases for further testing. So this is the full W model. Two V's with these arrows between the stages here, between the stages. Right, this is the W model. This is the final conclusion we told you in this lecture. This is, I hope, what you learned from this lecture. Alright, the W model is very important, so please memorize it. Okay, very, very important. So this is the lecture, the third lecture, the lecture 3. Yeah. Lecture 3 about CBD life cycles, and we learn we review different life cycles, right? And finally, we know what is the life cycle model of CBD, a W model, and you should know how the W model comes from, right? Okay, so I will leave you some time to to understand the knowledges from these slides. Okay, thank you very much. Oh, don't forget, there is a lecture 4 and a mini project waiting for you, so you should watch the other two. Okay, thank you.